All right, here we have another function from the natural numbers to the power set of the natural numbers. And here again, we will see that this function is not onto. And I want to emphasize that it's not onto many elements of the power set of the natural numbers. There's many choices that we could choose for this position here that this function does not hit. So there's many choices for getting a D and E here. But the absent bit string rule is systematic, and it chooses an exact one. And it always does the same thing. I mean, it doesn't always choose the same thing, but it always chooses something in exactly the same way, right? It goes along the diagonal and chooses the opposite value. And it's because it does that systematically that we can say that there's always going to be something, no matter what our function is, that isn't in the range. All right, so this function here, another way to write this function is f of x equals the complement of the set containing x. All right, notice that here, right, this is the complement of the set containing 0. I mean this right here, this one right here. Right, the complement of the set containing 0, it's all the natural numbers that aren't 0. And here we have all the natural numbers that aren't 0. And here is the infinite bit string representation of the set, of the subset of the natural numbers that contains all the natural numbers that aren't 0. Similarly, here we have the complement of the set containing 1. This is all natural numbers that are not equal to 1. And here you see them all right here, written out as a set. Here's its infinite bit string representation. And so on. All right. And so let's see. There are many possible things that you could put here that you can see that this function does not hit. Right, all of these, what you see if you look at all these here, right, is that they all have every natural number in them except one of them. So if we picked any subset of the natural numbers that didn't have two natural numbers in it, then it wouldn't be any of these, because each of these, well, all infinitely many of them. So let me just put them all in there. And so here's the ... getting the rest of them. They all have almost every single natural number in there, just not one of them, right? And the first one doesn't have 0, the second one doesn't have 1, this one doesn't have 0 in it, this one doesn't have 1 in it, this one doesn't have 2 in it. So if I pick a subset of the natural numbers that's finite, well then it's not going to be one of these, right? So let's see. Again, 1, 2 would work, right? That would give me a D and E here. What else would work? 1, 2, 3, 4 would work. That would give me a D and E here. But I want to emphasize that what we care about is that the absent bit string rule always chooses one that's not in there. Right, and as I said before, this infinite set here, this is the range. This is the range of our function. This is our range. Remember, range is always a subset of the target. The question is, does the range equal the target? And if the range equals the target, then we're on to. But the point is that the range never equals the target because of the absent bit string rule. Now, how do we know this is the range? Right, because the range is all of the outputs. And all of these have all of the inputs, all the natural numbers. So that's the range. All right, so now using the absent bit string rule, right, we go along. We say, okay, that's a 0. Okay, so we're going to have 1. That's a 0. So we're going to choose a 1. That's a 0. So we're going to choose a 1. That's a 0. So we're going to choose a 1. That's a 0. So we're going to choose a 1, and we'll do this forever and ever and ever. Now, what is another version? So this is the infinite bit string representation of the natural numbers. You see, the natural numbers will never get hit because the natural numbers contain every natural number. And each one of these, right, each one of these contains all but one natural number. So they're not equal. And so again, we're not onto.